Oh, hello. Welcome back to Turing Complete. Don't mind me, I'm just using the robot to explore the ship. Let's get back to it. We are kind of in the last section, the last sprint of this game, so let's get to it. Let's start with Hex Racer. This level is my second favorite pastime, converting hexadecimal to binary under time pressure. When dealing with a lot of bits, binary can become hard to read. Hexadecimal base 16 represents each combination of 4 bits in its own character. Toggle the bits of the level panel so they add up to the hexadecimal number in the question. You must beat level 3 to pass. So most people are probably familiar with hexadecimal because when you see a color wheel, usually online in like an online color picker, they will a lot of times show you the value in hexadecimal. Sometimes when computer programs crash too, you'll see a hexadecimal value. Usually that's like the memory location of the error. A lot of times you'll see memory addressed in hexadecimal instead of binary because yeah, it's easier to read. There's also base 64, which is used a lot, but I guess we're not doing that here, so let's not talk about it. Ready to race, start. Alright, I beat level 3. Great. Man, this is not fun to do. I can't do this in my head. I just can't. I'm not good at it. I understand hexadecimal in principle. I could convert if I really needed to, but not fast, not in my head. So really hard. But reach level 4. Okay, maybe we do delay next. All components have a delay, and in a circuit, the total delay is determined by the slowest path. This means you normally want to put things in parallel. In this level, you must prove that you understand this concept. Build the circuit with a delay of 6 and a gate cost of 5. Okay, let's see. So if I put them... Delay 6. Let's just... Oh, it tells you the delay and the gate up here. Okay. So you need... Delay store of 6. I can just have them up here, though. Right? Like, they don't need to connect to anything. Gate score 5, delay score 6. This'll work. Note you can see the delay path by clicking the hourglass in the upper right corner. Pretty simple so far. Up next, let's do RAM. Add a RAM block so the computer can address 256 additional bytes of memory. You need a way to decide which of the 256 bytes inside the RAM we are addressing. Select a register and wire it up so its value always selects the RAM address. When you later want to load or save the RAM, you will have to first copy the RAM address to this register. In this test, first copy from input 32 times and store these values. After you have loaded the 32 values, output them in the same order you got them. Outputting before you have read all the inputs will fail the level. Okay, I think maybe register 0 is the one we want to use to store values from RAM. So I put the RAM up, and I think everything should work. We might have a couple bugs in this program that I wrote, but this is just an initial setup. We're looping through the memory to save it all the memory backwards, and then once we save all the memory, we're going to start loading all the memory backwards in this load loop too. So let's just try it and see what happens. Okay, looks like the memory is loading properly. Ooh, I have a short circuit. So we're going to have to turn this one off if this one is on. Okay, I think it's going. Looks like it's working. Let's try this a lot faster. Okay. That was a tough one, actually. Memory is always tough. But yeah, this involved hooking a bunch of stuff up and writing some assembly programming. So that was a challenging one. I'm not sure I have it set up in the best way. In fact, I'm almost certain I don't have it set up in the best way. The way I have it set up here, I can only load memory into register 5, which is potentially a problem. But at least it works. Shift. To shift a value one left means moving all the bytes in a byte to the left by one position. The task in this level is to shift the first input to the left by the value given in the second input. The second input will never exceed 7. Okay, how do I want to do this? Okay, this is going to be really ugly, but I think I'm just going to manually wire these shifts, and that should work. Okay, unless I've made some error with the way I've hooked this up, which is entirely possible, this should work okay. So let's try it. Nope. Okay, so it doesn't like shift around. If it shifts off, it actually just becomes red there. So I just need to actually delete some connections and I should be okay, I think. Okay, let's try. Okay. In addition to giving you a shift left component, we also had the intern create a shift right component. All you had to do was to create a mirror of the version of this schematic. Easy enough. So I did it really manually here, but maybe there's a much more clever way of doing it that I'm just not thinking of. But this is easy enough. It works. I would recommend that you add the shift left and shift right to your hardware for future levels. Okay. Well, I'm sort of worried this is going to culminate in me just having to like rebuild the CPU yet again, but we'll see. Let's do the lab. Welcome to the lab. Like the component factory, this is not a normal level, but a tool. Programming on buggy hardware is very frustrating. It is painful to suddenly be forced to reason about circuits when you are in the middle of solving a programming problem. Therefore, when developing hardware, try to aim for 100% reliability before you start programming. Okay, so this seems like more of an informational level. You can do some error checking, I guess. Some debugging. All right. Unlocked all the 16, 32, and 64 components to use. Okay. Cool. I think that's it. Okay, let's check out Product of Nibbles. Multiplying two 4-bit numbers gives you an 8-bit number. Build a circuit that does this. Okay, so I think there's a shift and add algorithm. I think we shift these and then add this to this. I think this will work. I'm not going to test out like every single value, but like 4 times 4 is 16. That works. 4 times 1. Okay, that doesn't seem like it works. Let's test it and get it wrong. Yeah, multiply 0 and 1. Already fail. I think I'm going to have to refresh my memory on this because I really don't remember how it's supposed to work. This is just my guess based on what I remembered. So we will figure it out. All right, I've looked up the algorithm for multiplying binary. I've refreshed myself. I think I understand it. So if you think of multiplication, it's really like and. So right here, if you think of red is 0 and green is 1, right? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. Only 1 times 1 is 1. So we're going to end up using a lot of ands. Alright, so we've multiplied each bit over here by each bit over here using these ands, and then we're combining them into bytes, like using a byte maker here. And now we just need to add these together. Alright, and then this result should be our final multiplication number. Let's try it out. So 1 times 0 is 0. 0 times 1 is still 0. 1 times 1 is 1. Alright, so I think this is all working properly using this multiplication, then shifting, and then adding everything together. It's one of those algorithms, oh, we missed the connection here, that is probably near impossible to figure out yourself. So I had to look it up, but I think it works. So let's try it. No, I got one wrong. Oh, this is hooked up incorrectly right here. Let's try that again. All right. What you did here was actually multiplying two 4-bit numbers. We had the intern scale it up to bytes instead. All right, cool. And it looks like I had gotten an achievement for that. Awesome. And obviously we could have done this using the left shift component that we built earlier, but I think looking at it like this actually makes more intuitive sense. Like I think I understand it better just doing it this way, with using just, you know, ands essentially and some additions. I kind of like doing things the more kind of conceptually straightforward way. So I'm actually really happy with this, how this turned out. Okay, I suppose we should just finish up with divide. Integer divide two numbers to find the quotient and the remainder. Consider the fraction 7 divided by 3. 3 goes into 7 2 times and 1 is left over. Here 2 is called the quotient and 1 is called the remainder. Okay, so it looks like we get to do this by writing software, which is actually really nice because trying to do a division by building a circuit, kind of like we did with multiplication, is like really hard or complicated. I really have no idea how to do it, but this shouldn't be too bad. Okay, I think I've got this. It's really just a matter of whether I'm juggling my registers, my values in my registers properly. All I'm doing is I'm basically subtracting your B value, the bottom here, from the top, and adding 1 to register 5, like keeping a count until it goes negative. If it goes negative, then whatever is remaining is the remainder. If it goes negative, it jumps here, and then it puts the count and the remainder to the output. Again, it's just a matter of whether I'm juggling these correctly, so we'll see. Ah, no. Oh, okay, so I think I see the problem is that this jump less than 0 isn't working. It only works with signed and not unsigned integers. But this test is supposed to work for unsigned integers. Okay, so I'm going to rewrite this whole program in the leg CPU architecture rather than the Overture CPU architecture. I think this should work better because this does comparisons on unsigned integers, which was the problem in the Overture architecture. So maybe I could figure something in with Overture out, but I think it would just be easier just to use this CPU, and it'll probably be better for problems in the future as well. I'm not entirely sure this is going to work, but I'm pretty much just doing this same thing I was before. I'm initializing register 5 as a counter, and putting the inputs to register 0 and register 1, and then if register 0 is less than register 1, it just jumps to this get remainder section, which moves the counter value to the output and then moves whatever's left over in register 0 to the output. Otherwise, it just subtracts and then adds 1 to the counter, and then I think this should just work as a jump back to this label. So let's test it out. No. Okay, I think I maybe worked out all the bugs. Let's find out. Oh, yes, thank God. That was the biggest pain in the ass level so far. But it works. I'm really happy it works. It looks like we've gotten these division circuits here, which is interesting because we haven't actually built a division circuit, which is fine by me because those seem really hard to make. So, all right, onwards. So probably a good idea to pause here for now. I'm assuming stack, push pop functions will probably take a while to implement. So I will finish up this track next time.